I'm going to share you a few works that well, so two of them are already published and one is work in progress, which I hope will give you some more fresh ideas on this field. I'm going to talk more in general, the approaches in general, but we do have some applications and some of them include biomedical images. So let's start. So we have three main topics for today. First one is we are going to talk about the alignment of multi-layer features, then how to transfer learning, especially learning of representations with fewer labels. And finally, this is the work in progress. I'm going to talk about self-supervision in the context of semi-supervised feature learning. So this first part was already published in 2019. It's work in collaboration with my PhD student, Fernando Santos. So we already know that CNNs are very good for transfer learning. So in terms of transferring image, what we have learned in image content, they are capable of finding hierarchical and general purpose visual features. However, the problem is when the target domain that we want to use those features are far from the original one, usually the ImageNet challenge content, we have problems because as we go closer to the output, which are the layers that are usually employed in such systems for transfer learning, we have more domain-specific semantics. So semantics are more related to those 1,000 classes that compose the ImageNet challenge dataset. So we already know that for a while, maybe 5 years or so, that the bottom level layers, I mean the first layers, when we look at what the convolutional neural network has learned, contain more local information, they are more generic, because the filters, they act on regions of the image that are usually 3 by 3, or if you go to the next layers, then the regions are 5 by 5, 7 by 7, because of the local receptive fields that increase as we go along the network. Then when we look at those features, they look like this. Oh, I'm sorry, I think I just used the wrong tool. Yeah, that's correct now. So yeah, so those as in this case, they are basically learning what are the flat regions, colors, blobs, and filters that resemble Gabor filters. As we go to next layers, then those regions are combined so that the filters are actually learning specific textures and more complex patterns. And as we go, they resemble much more something that, in this case, there are objects in the scene, so images from natural scenes. In particular, here we have a teddy bear. So in the 8th layer, we can see that this resembles actually the class that was trained on. So one thing that's important, that is bottom layers are much more generic, but they contain local information, while top level layers are global descriptors of the whole image. So when we get that feature maps or the activation maps from the last layers of the network, what we have something that all activations were computed considering the whole image. So we consider that a global descriptor of the image. So the first question that we started to investigate a few years ago was, are those initial layers useful to improve the discriminant discriminative capability of the global features for image classification. Why is that? Because usually people use such last layers or layers of the top of the network as a way to extract features from pre-trained networks. Then our system here, which was published in this paper, has this setup. So assume we have a source data set from which we want to train some classifier. So this source data set, as it goes on this flow here, is going to be used to train a classifier in the end. While our target data set, we assume we have few instances that are actually labeled. So we cannot use them to actually train a network, but we can use, for example, to test. So it goes in this direction here. So we have this purple squares here, and then in the test set, we look at the accuracy. So the idea is we want to use the source to train a classifier and see if this transfers well to a target data set. And we are going to do that by performing a fusion with a global descriptor that comes from the top of the network and a local descriptor that comes from the beginning of the network. In this case, is a residual network with 50 layers. And we are going to use a manifold alignment technique that is called TCA, that I'm going to explain later. So we use the ResNet 50 for getting the activation or feature maps. And we are going to use the first 3 residual blocks for the local features. And the output of the average pooling layer, the last one, just before the prediction, so just before the layer that actually does the classification for the network, we are going to consider that a global descriptor. This is usually the standard way of extracting features from pre-trained networks. The global features has around 2,000 attributes, while the local features, and this is a problem, have much more because we are processing patches of the images. So in this case, one of the first residual block outputs almost 800,000 attributes. So we have to deal with that. We have to, in a way, select those attributes. We are going to do that as well. Then we are going to perform a multi-layer feature fusion, considering those both the local and global features, and see how it improves our final representation. We investigated a few techniques for this feature selection, for the local feature selection. A very classic technique, so principal component analysis, selecting the M principal components from all the features. We also have this idea of flatten and pooling, so we just flatten all the feature maps, and then we get average of sequential values. And what is also something that's common in the literature, especially nowadays, using the global average pooling, which is for each feature map, we average out all the values, and then we get a scalar or a single value from the whole feature map. The technique that is used in this paper, and it showed that really make a difference when using both the local and global descriptor, is the transfer components analysis, or TCA. This is a technique that is related to PCA. It also uses the same theoretical background. However, it transforms data so that it correlates the axis of different data distributions, or actually data distributions that come from different sources. So if we just use, for example, two distributions here, two sets of data, they are colored here in blue and red. And if we perform the PCA, the 1D latent space will look like this. So we have the blue data set projected in a region, and the red data set projected in a different region, although they both contain similar, they contain data that come from the same classes, so they should be overlapping. TCA does exactly this, so it tries an overlap of those two distributions, so it projects into a latent space that considers the two distributions at the same time. So the variance of these two distributions at the same time. So it keeps the maximum variance of both data sets aligned. We tested this approach that combines the local global features using the manifold alignment with 3 data sets. The first one is a simple one. It's a fruit domain. So we have as a source data set, a data set that has classes of 360 different fruits. They are all well segmented, so those instances are very well behaved. So we wanted to know if we could train on a very well behaved data set and then test how this would transfer to a more realistic scenario in which we have multiple fruits, different illumination conditions, contrast, and other issues. So those are 2 different data sets, however, they share the same semantics. Another data set, the similar idea is the office domain. We have the Amazon data set on the top, which contains e-commerce images of different objects, and the webcam data set that has those same objects, however, they are in their habitat. So they contain background, clutter, other objects that may make the problem more confused. And finally, the skin lesions domain. So in this case, we have 2 data sets, a larger one, which is the HUM 10,000, which has 10,000 instances of skin lesions that we are going to classify between non-malignant, which examples are on the left-hand side here. So this is just common nervous lesions, so non-malignant, and those are melanoma lesions. We want to transfer that to the PH2 dataset, which has much less instances. In this case, I think it's around 200, just 200 instances. So it would be impossible or unfeasible to train a network from scratch for this data set. So this kind of simulates situations in which one hospital or one place has collected images, but not sufficient to train a classifier or deep neural network. So we wanted to see if we could get a larger data set and then transfer what has been learned to this new target data set that's a local data set. So just to get this overview again, so let's say that we have a source data set, so the HAM 10,000. So this would be our source, and we are going to extract from the source both global, local features, and then the target data set, which has much less images, let's say just 200, and we are going to align them and perform a test using the SVM. The idea of using an SVM here is for us to evaluate how linearly separable are the classes. So the idea is not to use a classifier from the actual network, because we just wanted to see if our approach improved the linear separability of the representation. So we use 2 setups. First one, just use the ImageNet weights. So as it is a common approach. So we just fine tune the image from the ImageNet weights coming from using the source data set. And only the last 7 layers we're allowed to adapt to the new domain. We have seen that in a previous work, that it's better not to try to train all the network if we have a very different domain. And also, we also explored not using pre-trained weights, just not fine-tuning them, just using the pre-trained weights. I'm going to show you in a few slides. So we evaluate also, because the TCA allows us for a selection of different number of dimensions. We tried with 256 and 64 in between those two. We also use the TCA, use the RBF kernel, because it, as with the PCA, you can use kernels. And the SVM as a classifier, it is a linear SVM, no kernels involved, just to check or to evaluate this linear separability. So those are the first results. So don't be scared, it's a lot of them. What you should pay attention to is that we have this, our baseline is this first column here. So this is what has been used in the literature to extract features. So if we just get the ResNet and with the ImageNet weights and extract the features, for this case, the average accuracy will be around 30%. We average out different dimensions, so this from 256 to 64. However, if we enhance this, if we enrich these global features by fusing with the first, second, or third block of the network, we are going to get an improvement of around up to 8.5% or so, 8% improvement. So this showed us how we could improve the global features by using local information. If we use fine-tuning, this improvement is even better. So we could, by fine-tuning the network, this gives us further 3% or so improving in this fruit domain. This is the same for objects. So in case the office domain, we also see some improvement overall. And for the skin lesions, it's the same, but then now in this case, we note that we have to rely on more on larger features, to a larger number of features to be able to compete with the global features. So this gives us around 2% increase in the final representation. So this is the main accuracy, the gain in accuracy from using manifold alignments compared to not using them. So if we use the image directly, the ImageNet weights, and those are the 3 different selection methods for the local features, we can have an average improvement of 8% around all the data sets by using the first block, 6% using the second one, and 4% using the third one. But if we fine-tune with source data, so if we do have, so the first case is basically don't have, we assume we cannot fine-tune it. But if you can fine-tune it, the improvement is even better. And we note also that usually the first layers seem to be very good in this case, because as we approach the final layers, it becomes much more and more resembling the global features, so it doesn't make much sense to make this fusion. So a few remarks on this work. So manifold alignment between local and global features overall improve linear separability of the representations in the case of transfer learning. Some data sets that are more fine-grained, I mean, the images look much more like they resemble each other. So in this case, fruits and skin lesions may require fine-tuning. So we, by using just the the pre-trained network, we may not see the improvement as well as we do with fine-tuning. Of course, this gain comes with an increase on the computational cost because we have to process local features. But note that we can reduce the dimensionality of the final embedding, so that can be used to index images in a large database, for example. And also with clutter and large intra-class variance, the addition of those local information become less effective. So that's what we see with the Othce domain that gave us the little improvements in some situations. So we think that the clutter and the larger intra-class variance caused that. Right, so next we are going to talk about transfer learning with fewer labels. In this case, we have a similar scenario with respect to the previous work. However, here we are trying to make explicit use of the unlabeled instances. So in the previous case, we just work with we assume sometimes we didn't have the labels. However, we always in the end we trained it with all labels available. So all the source data was used to train, and all labels were used to train. For example, in the HAM 10,000, we used all the 10,000 instances, labeled instances, to train the SVM classifier. Here we are going to work in a scenario in which we assume we do have less labels. So what happens when we decrease the number of labels? This is already also a published work in neural networks last year, and in collaboration with Fernando, which was my PhD student, and also Jemre, Joseph Kittler, and myself. So the idea is transfer learning from a source data set to a target one when few labels are available is a scenario that's much more challenging. And previous work studied semi-supervised settings by using label propagation, for example, which is very common to propagate the labels that from instances that we know from the ones that we don't have labels. And always, or in many cases, assuming that we have the same distribution for the data and for the relationship between the data and the actual labels. But what if we have the same classes, however, P of X and the relationship between the X and Y change from the source to this target data set? So the idea of this work is to learn features with a source XO. So, and then in P of Y given XO, and then use what was learned from those distributions with a target P of X of T and P of Y given X of T. In this case, we have three scenarios possible because we assume as I talked before, we assume we could have scenarios of not having any labels at all, so it's a fully unsupervised. So in this case, what we use is a reconstruction loss. I'm going to talk about that in a bit. So the reconstruction loss is for a network is based on an autoencoder. So we are going to use an autoencoder that gets as input the image X, and then tries to reconstruct this same image X hat. So it's classical autoencoder. In the second scenario, the other extreme is that we have a data set that's fully supervised, so we can use just a regular CNN and use a classification loss. And what we investigate in this paper is the combination of those two. So let's see, we have an embedding that we choose. So the CNN or the network is an encoder that maps the image input to some embedding. And we use this embedding to both classify it if we have labels, that gives us the first loss. Or if we don't have labels for this instance, we can also instead of classifying, we can try to reconstruct it and then get the second loss and then combine those two. So this is something that has been investigated in a few applications, but at the time of we wrote this paper, not in the context of transfer learning, and also not by using those at the same time. We also combine that using a new loss function. This actually not a completely new loss function. The loss function is basically what we propose here is a way to combine those. So let P be a proportion of labeled instances in some source data set. So we assume we have from 0, so no labels. So this is just a deep convolutional autoencoder. And P of 100 means we have a fully supervised, so a classification CNN. And everything in between is what we investigate in this paper as a novel approach. The weights are computed as follows. So for we have two branches of the network, a branch of the network which is supervised, the CNN, and one which is unsupervised, which is the autoencoder. So we weight those by using this idea here, which basically gives us a proportion of the labeled instances. So we call that weighted label loss. And so it has the first loss is a classification loss. The second one is a reconstruction loss. Look that the first one relies on labels. The second one relies on just the image. And W of sup and W of unsup are the weights that we compute using this first one. So we evaluate that using digits, data sets of digits. So we use 3 of them. This is very convenient because it's very well behaved. First one is MNIST. Second one is Street View house numbers. And third one is USPS. We can see that although the second, the SVHN is a digit data set, it is it comes from images that were taken from house numbers. So this is carries the same semantics, but they can be very different and even have clutter. So parts of other digits. So it's a much more challenging data set in this sense. So we want to see if we could, even though we have a different acquisition scenario, we could transfer those features. The second one is natural scenes and objects, CIFAR 10. It's a classic data set for classification, and also the STL10, which is interesting because STL10 actually has almost all classes, shares almost all classes with respect to CIFAR 10. So the first 9 classes are the same, but the last one is different. So CIFAR has a frog class, while STL10 has doesn't have a frog, but has monkey classes. And interestingly, the STL10 has 100,000 unlabeled instances and just 500 labeled images. So this is very interesting for us to study because it's a data set that is that was designed to test semi-supervised scenarios. So just to recap, our idea is to compute 2 losses from an image. We can compute both losses if we have a label. However, if you don't have a label, we can compute loss 2 and then still combine them using the WLL loss function. If we do have all labels, so if you have a scenario of P100 and we use our loss, so that means we also use a reconstruction loss to guide the process of learning. We could reach very interesting results. So this table here, S means source and T target. So when we use MNIST as source and SVHN as target, what we have is an accuracy of 74%, which is far from the state of the art. But this state of the art here is fully supervised. So it uses the actual SVHN dataset to train and to test. In our case, we don't see at any time in training time any SVHN images. So it's quite remarkable that we could reach this high accuracy. For the other data sets, for MNIST and USPS as targets, we do have very good results. In this case, comparable or much closer to the state of the art. So we could reach up to 97% accuracy on MNIST, which, okay, I acknowledge that it's not very difficult to reach, but in any case. And for the USPS, 90% in comparison to 95 of state-of-the-art supervised method. And it's what's more interesting here, and this is the main contribution of the method, that we can we have both extremes in this case. So we have fully supervised scenario, and we have a fully unsupervised scenario. So in between those two, so fully unsupervised, let's see here with using the SVHN dataset, fully unsupervised, we have just 50% accuracy, and fully supervised 74. And for the MNIST, well, the MNIST is much easier to solve, and for USPS. So yeah, let's see what can we get in between those two. So the first one for SVHN, as we add just 10% of the total of labels, we improve that to 72%. So that's the increase that we have by using the unlabeled instances and enriching this training with just 10% of labels. And it's interesting also because it goes up like rather smoothly. Sometimes we have a few decreases here, but overall we start to increase this until we reach the supervised accuracy. It also happens similarly with MNIST and USPS as well. So this makes the approach useful in cases that we want to add labels on the top of a lot of unlabeled scenarios. I'm going to show you also the results for the STL case. Remember that the STL was designed for semi-supervised learning. Then we have a test here which uses just the STL. So actually, it's not actually transfer learning here because we are within the same data set. However, we always just train with the training set and test on the test set. So all targets here are test sets, and all source here are training sets of the original data set. So when we use all the STL unlabeled data in training data, and we test with whole thing labels, so this was kind of an ablation study to see how the actual hour loss, our waving procedure helps with this learning process. So we do improve it from 49% to 52, which is quite good because we are just basically changing the weights of the losses. And by using as source STL and as target the CIFAR data set, in here we can see that we did two experiments. The first one just includes the 9 labels that were shared between STL and CIFAR. So we call that CIFAR 9 because we didn't use a frog class. And we also see some improvements. And by considering all classes, so we actually have 11 labels here. We also improve a bit. So even in conditions in which we hide one of the classes, we could still learn something and improve with unlabeled instances. So final remarks on this work. The semi-supervised setting is applicable in partially labeled source to target data. Weighing the classification and reconstruction losses using the proportion of labeled examples seems to help making better use of the unlabeled ones, because we improve a lot on what has been learned using just the unsupervised version. And the gains can be seen in both training from scratch a network and also using pre-trained deep networks. So finally, this is more recent work, so work in progress actually. So we are just in final preparation of a paper that's we're going to share as a preprint and then submit to a journal. So this is semi-supervised self-supervision feature learning. Actually, what we did in the previous work can be considered in some sense self-supervision, since reconstruction loss is basically, it doesn't require labels. So we just rely on the input data. But since, well, 2 years ago or so, this self-supervision field became much more like, became a field by itself. So the idea of making, in computer vision, I mean, papers starting to appear in major conferences, talking specifically about how to get an input and then compute or make up some tasks that are auxiliary tasks and doesn't require label. Reconstruction is one of them. So this is a work with a student of mine, also Gabriel Cavallari, and we call that semi-supervised self-supervision for robust feature learning. So we use unlabeled data. When we use just unlabeled data for some data sets, it offers us little improvement. We see that in the previous work. So sometimes accuracies are not great. And when we go to extreme scenarios of availability of labels, let's say 5% or less, are much more challenging. You note that in the previous work, we used from 10% to 90%. In this, we are trying to see if we could use even less. And also, we note that under scenarios of attack and perturbations, the network may overfeed for labeled data and ignore unlabeled ones. So this is a problem in some cases. So how using alternative tasks, self-supervision, may help improving representation learning under attacks and under such scenarios. So we invest here, this is the first attempts that we did. We actually have more experiments, but I'm not going to show you here for brevity. So we investigate this scenario. We have this STL data set again here, in these first two images, the STL10. This is the fashion MNIST data set, which was designed to be similar to MNIST in terms of number of classes and also grayscale images, etc., but has fashion items. And the third one, we investigate a biomedical data set, which is for detection of malaria in blood smear samples. So what we have here is a pixel attack on these data sets. What this means, we insert a pixel. I don't know if you can see here. Those pixels are white pixels in this case. We just did the simplest attack possible. Those are placed in the same place, in the same position, in using the same RGB value for the same class. So for airplane, for example, they always we are going to appear at the same position and using the same RGB value. For other classes, let's say the truck class, the same pixel will appear but in another position and with another RGB value. This may lead may show us how the CNN can overfit by using this pixel as a target feature to learn the concepts of airplane in the other classes. So I just zoomed this to show you that trousers here in this data set has this pixel in this position in all images on the training set, not on the test set. So just on the training set. So we investigate that by using just 1% of labeled data and the STL10 data set. And we use two architectures, very well popular architectures, MobileNet v2 and HasNet 50 v2. By using those architectures as pre-trained networks and using just 1% of data, labeled data, without any attack, so we have the two scenarios here, no attack and the pixel attack, we can see that the MobileNet didn't even converge because we have 10 classes and it gives us 10% accuracy. With 1% of the data, it's not possible for MobileNet to converge. The HasNet has some signal here, so we do have an improvement in accuracy. However, we could see that with pixel attack, this decreased a bit. And remember that we use the most dumb kind of attack in this case. By using the semi-supervised scenario, that means we are using something that's similar to what we did in the previous paper, but in here we are using another, instead of using the reconstruction loss, we are using another one. I think I had this slide here. Let me check. No, I don't. That's unfortunate. I'm sorry. I forgot one slide here, which is the whole architecture. But basically, instead of using the reconstruction loss, what we do is that we use a loss that is a classification loss. So we have two classification losses, one for the actual classes and one for rotation, which is the most basic self-supervision technique used. So we compare, we have 10 classes, the actual classes from the data set, and we have 4 classes for X auxiliary task, which is 4 rotations of the image. So the network at the same time tries to find out what is the class and what is the rotation of that image. So 0 degrees, 90 degrees, 180 degrees, and so on. All right, so with this setting, so by using unlabeled data, this unlabeled data just relies on the 4 rotations. We get a significant improvement. The MobileNet even could converge in some sense. And without attack, we could reach 44% of accuracy with just 1% of labels. Of course, with pixel attack, this decreases a bit, and this is the delta. That means the difference or the gains in accuracy when using our approach all looks very good in this case. For the fashion data set, because it's an easier data set, but even though it's easier, MobileNet couldn't converge. The HasNet came up with good solutions, but we can see here that the pixel attack makes a greater difference. And with our approach, we could improve both scenarios. And for the Malaria data set, we've seen similar results. So in this case, the Malaria data set is just, well, it has Malaria or doesn't. So it's a binary data set. That's why in this case, it's 50%. Without the attack, we made we make this learning something useful, because for using just 1% of the data, and if we have the attack, well, a binary case with the 60% of accuracy is not useful. But if we could reach up to 90%, then it became useful. So we can show that our approach makes it viable to use this data set with just 1% of labeled instances. And this is a projection of the feature space. This case is the SCL10 under attack. So in the left-hand side, we have the features, well, the 2D features projected using TSNE for the 10 classes using a regular CNN. In this case, we have an accuracy of 41%. You can see here the colors are the classes, so it has a huge overlap. So those two classes here, cyan and blue, are hugely overlapped here. Also with the green ones, even this here, so magenta and red are actually overlapped, and so we could see that this accuracy makes sense from these features. We have a huge overlap between the instances, and with our approach, we could improve in 10%. So you can see here that this region is much less, it contains much less overlap. So it started to learn something specific, that's class specific. For those regions here, we can see that it can separate some classes. Although it's not perfect yet, of course, it's 51% on a 10 class data set. We can see that we have room for improvement, but it seems very promising. So this is work in progress. It shows benefits of using self-supervision loss even for 1% of available labels. This also makes the feature space more robust to attacks. So it improves both regular scenarios and scenarios of pixel attack. And there's lots of future work to do. So I think this is a field that is very hot. It's a very hot topic in the major conferences, and we really are interested in studying how to use more and more self-supervision to improve feature learning under different scenarios. So to conclude it, to obtain good features under transfer learning and scenarios of scarce labels, the message here is consider manifold alignment between local and global descriptors, and consider manifold alignment in general. So when you do have, it's working with different data sets, even though the data sets are similar, but they come from different sources or using different equipment, manifold alignment can really help. And also use alternative losses to allow using both unlabeled and partially labeled data, as we have seen in this various examples that it has lots of potential. So if we didn't understand parts of what I talked here, so I want to point to you a tutorial paper that we published a few years ago, but it's still updated in terms of deep learning for computer vision. And then, but if you do understand everything and we want to know more, those are the papers that were published with our in our lab. So the first one, second, and the third one, which is not available right now, but I think in 1 or 2 weeks we are going to circulate that on our channels. So that's it. Thanks very much, and I'm open for questions.